All right, so it's a little after 3. Why don't we get started? So today our speaker is Ratliff. Ratliff. All right, and yeah, really excited to see this talk. And I was telling her earlier, I saw some of the preview on some of the slides already, and I can't wait to hear the dialogue backing up some of the content that I saw last night. But he's an associate professor of electrical engineering and computer engineering at University of Dayton, Ohio, and also the director of the Applied Sensing Lab, founded in 2000. Received his bachelor and master degree in computer and electrical engineering, also from the University of Dayton in 2000, 2001, and his PhD in electrical engineering from University of New Mexico in 2004, and was the recipient of the 2006 University of New Mexico Hope Joy Dissertation Prize. Congratulations on that. Yeah. His research interests are in the areas of image processing and pattern recognition for remote sensing applications, particularly in the areas of polarimetry, hyperspectral, IR, and 3D modeling. So that's sort of in line with a lot of things that we do here. So it's a nice coupling between the two groups. Prior to his academic appointment in Dayton in 2019, he worked in industry, supporting various agencies in the DoD, primarily with AFRL sensors and some of the areas in and around that. His work is primarily focused on remote sensing topics, many of which we're going to see today in the area of polarimetry, HSI, 3D modeling, with applications related to tracking and ID within intelligence, surveillance, and reconnaissance. So really excited to see that.
All right. Well, thank you very much, and thanks for having me here today. I'm excited to be here. And really what I wanted to focus my talk is on kind of the lab and field capabilities that I've been working. So as Emmett just said, I have been in my academic role for, this is about my 6th year. So I've kind of spent the last 5 years just building up kind of a remote sensing lab and remote and these capabilities. So that's kind of what I wanted to talk about today. There we go. So yeah, just a quick overview. I want to talk a little bit about kind of an overview of my lab and a bit of my history, but then I want to focus in on some of the kind of more unique capabilities that I've put together in my lab to support remote sensing phenomenology research. Then at the end, which I may have to speed up through a little bit, just to give you an idea of at least some of the active applied research examples that our lab is kind of facilitating, so on and so forth. So as I already mentioned, I switched over from industry to academia in 2019 with kind of the vision and goal of building a remote sensing lab and research program at the University of Dayton. And I particularly focus in the EOIR region of the electromagnetic spectrum for the most part. But the first thing I did was apply for some grants. I got pretty lucky and won a number of them that let me really buy a lot of the equipment that the lab is based around, that I'll be talking about. And then my university, because of that, let me kind of design and build a new lab from the ground up. Since I was able to get a lot of field collection capability, I realized that I needed a way to get things to the field. So I was able to convince my university to further let me buy a shuttle bus and kind of hack it into my mobile lab, which I actually drove up to RIT back in August during the ROCX data collection. So I'll talk a little bit about that too. But I think overall, just especially where we're at in Dayton, with the Air Force being headquartered there, there's a tremendous amount of remote sensing research that happens, in and around the Dayton area. So I was just trying to provide an academic space to really facilitate and support all the activity that happens in the area. And it's really about a lot of experiential learning. So getting a lot of students, working to help plan and conduct data collections to facilitate their own research, having our own sensors. I wanted to be an academic that had a lot of capabilities to support that type of stuff. So just a couple of quick shots. This is what I call my collaboration space. It's just a nice room where my students, where we hang out. And then this is a shot more of what I call the applied sensing lab. So when I designed this space, we can, and this is what I'll spend a lot of the time, a good part of my um, talking about is this particular room. So I'll save that. We're just having facilities so we can, integrate sensors and build payloads and things that we're going to be flying, in addition to have, nice storage and processing facilities and things like that. Um, but when I won my initial grant, the equipment list that I had was, my background is pretty heavily in imaging polarimetry. So I wanted to be able to do, imaging or have polarization or imaging polarimeters and, the visible and in the long wave. So we have a number of those. We also were able to get a SWIR HSI camera. And I have a number of different 3D imagers, from light projection scanners to time of flight cameras, but we wanted a nice terrestrial LiDAR, so we were able to get one of those. And but then the other big piece of my grant was just making sure we had enough, to do at least, you know, maybe not what Emmett does, but doing enough radiometry to be dangerous. So just having an integrating sphere and black bodies and ASD field specs and calibration panels and all the other stuff that we would want to take out to the field to do remote sensing collections. So the room I mentioned is what I call the Automated Remote Sensing Solar Simulation Lab. So that's what I want to talk a little bit about. But before I do that, I wanted to provide a little bit of motivation because the title of the talk had scene generation in the title, and that's just sort of my own self-imposed title for what I'm calling what I'm doing. But typically, and I think most of us who work in the remote sensing world know that real data is really where it's at, right? You want as much data from the sensors you care about for your application as you can, realistically get but the problem is there's never enough of it, right? We never have enough data. It's difficult, it's expensive, right, to fly or to do airborne collections. It's hard to control and isolate parameters in practice, right? The sun is always moving, the atmosphere is always different, right? Even if you repeat the same experiment tomorrow, something is different, right, that you can't control. So repeatability is hard. Truthing is always difficult on real data, and this is especially true for polarization. A lot of times we don't really know what we should be seeing. So then you have on the other end of the spectrum, tools like DeerSig that are, are great at especially good at generating synthetic data. So I say it's more cost effective eventually, right? I mean, DeerSig wasn't a cheap tool to build, but once you have it, right, to produce data can be pretty cost effective. And of course, there you get a lot for free, right? You can control and isolate parameters of interest, high repeatability, right, to repeat your experiments. Ground truthing is a lot easier because you have 3D models you're working from, so on and so forth, right? With the major caveat is a lot of times what you get from it can really help you with phenomenological studies, but oftentimes it's still synthetic data that maybe doesn't capture the full stochastic nature of the problem space. And sometimes you've used that to develop and test algorithms, and then you find it doesn't translate as well as you want to the real data domain. But of course, it can do great things for you, and it can satisfy data augmentation needs and all that good stuff. So what I was aiming to build inside of my lab was kind of a middle ground in that, and that I want to use real sensors, I want to use real light, I want to use real objects, but do it in a controlled sort of way that has a lot of the benefits of synthetic data, right? And that it can be cost effective, that we can control and isolate parameters, that we have high repeatability. Truthing is a bit easier with the major caveat is it's not synthetic, actually, right? It's real optical data from the same sensors we're going to take from the lab, put on a drone, and fly in the field. So that's kind of where I'm going with this. So with that said, that was largely my motivation for the Automated Remote Sensing Solar Simulation Lab. The real idea was just to build a facility with a lot of positioning devices where we can position very accurately and repeatably light sources, sensors, and objects, right? And in a very controlled way. So the robotic arm you can see that I have is what I call my sensor positioner. There's this coordinate system that's at the center of the lab, and the whole idea is that the robotic arm can position a sensor very accurately and repeatably within that coordinate system. There's a high precision rotary stage under this model here that allows us to rotate the scene or objects. And then I have a couple of different light sources. So on the ceiling here, you can see this is an array of artificial skylights. So they actually have some specialized optics. They're largely architectural features that are meant to mimic kind of the diurnal cycle of outdoor ambient conditions. And when I saw those, I thought that would be kind of a cool thing to use in a lab to control and act as kind of a diffuse downwelling light source. So we've had these, and I'll talk a bit about the characterization and control of them a little bit later. But the other thing I wanted was to be able to essentially put a collimated light source and be able to position that as a function of azimuth and elevation within the coordinate system. And that was something that didn't really, or if there were solutions, they were probably too expensive for me to buy. So I worked with some of our capstone mechanical engineers to kind of design this system. And then I'm very lucky that I have my dad who's good at fabricating things. So then the two of us kind of built this system, which I'll talk a little bit more about. I haven't really done much with this yet, but I did hang a haze machine in the corner with the idea that we can close the room and maybe introduce some level of atmospheric obscurant in the air for, which is kind of interesting for polarimetric studies. But just showing, I use pretty much for all my positioning devices and stepper motors and things, I use Zaber. I like their products, but this is just showing what those models are. Our robotics lab got a new donation of robots from Motoman, so they had a bunch of robots available. So then they asked me if I wanted one, and I said absolutely. So that's why I have kind of an older MH5F Motoman robot that we use for our scene positioner. As far as the solar positioning system, you can see basically it's a system where there's another one of these Zaber high precision rotary stages upside down on the ceiling that allows us, that acts as our azimuthal stage. And then the mechanical students helped me kind of design this winch system. So I had this curve track fabricated, probably not nearly as precise as what's in Dr. Bachman's lab for his rotary stage. But, basically this stepper motor will pull this cart up and down the track so we can control elevation. So between both of those, I have a fully automated way of positioning a collimated light source within pretty much anywhere within this hemisphere. Just right now, like I say collimated light source, but it's actually not. It's a fairly cheap LED flashlight, like high lumen flashlight that I bought off of Amazon. So it has a convex lens, which means it has beam divergence, which are all effects that we've characterized. But if I truly wanted a collimated source to illuminate my entire optics table, that wouldn't work out very well for the space. But that's what our current generation collimated source is. And then these skylights that I mentioned before are manufactured by a company called Interscene. They're a relatively new product. It's their virtual sun product. So they have a fairly wide spectral response in the visible, and they basically consist of 4 different channels of LEDs that we can mix at different power levels to create different or simulate different solar irradiance spectra. There's technically a 5th channel that creates this artificial sun. So when you're standing there looking at them, they're kind of neat because they're coated with these optics that actually focus that channel at infinity. So you only see that sun in one of the lights. So it kind of gives you this effect as if you're really seeing the sun. It's kind of neat. But of course, I have my own sun, so I turn that channel off and we never use it other than to show people because it's kind of neat. So, but we've used our ASD spectrometer to characterize both our direct source or flashlight essentially, and as well as each channel using the remote cosine receptor to measure kind of the response of each channel of our LEDs. And then we've worked through some different, well, first we wanted to look at what is achievable from a color perspective by mixing all these different LEDs. And then we've parameterized it currently by correlated color temperature. So you can see that we can for sure mix the colors to get the full daylight curve, which is mostly what we're interested in terms of the lab. So we've worked that out and can parameterize the skylights in terms of our experiments, things like that. We've also kind of looked at, what if we were to do some Modtran runs, under different aerosol conditions, things like that, to get us an actual solar irradiance curve. How achievable is that by mixing these lights, to give us more flexibility in how we would want to control the lighting in our lab? And we found that, that just the lights, there's a little bit of dip between blue and green that will probably be a little bit problematic, but it works better given that we only have 4 colors of these LEDs to work with. I think it works better than we thought it would. But as mentioned before, we have at least a decent set of calibration devices. So we've been working to characterize our sensors. I was talking to Emmett earlier how I'd love to have a monochromator and some other great pieces of equipment that he has. But we're at least able to do quite a bit of characterization work and do some basic radiometric calibrations of our sensors. And we deal a lot with polarimeters, so we have a lot of polarization components that we can use to further characterize our polarimeters and things like that. But I spent a lot of time, I have a pretty strong software background, so I spent a lot of time figuring out how to develop kind of an underlying infrastructure to control all of this. And what I came up with was, all my devices, at least in the lab, I can stick them behind a Raspberry Pi, which is running Ubuntu, and I wrote a simple server that runs on that. And the whole idea is that, for each one of these devices, I can encapsulate the hardware kind of behind the server, so that it's kind of a very scalable architecture. And then I'm just basically passing messages to these devices, right? If it's a positioning device, I can pass a TCP message to tell it to move to a certain location, or if it's an imaging sensor, I can control it and collect images, and everything gets kind of passed. And then I have kind of a main GUI that I've built that allows me to connect to these different devices and control them. So this is just an example showing connected to one of my imaging polarimeters where I've set up all of its parameters, and then it lets me collect an image, and then I can make sure that everything looks reasonable before we start an experiment. But I think the real power of the whole Ars Lab framework is this experiment creation button. So now that I have all these devices to where they're fully automated and can be controlled, you can actually just design experiments, right? So the idea is I can connect to different sensors and control or parameterize them how I want. And then I can just start, across the different positioning systems, right? So for example, if I want to build an experiment where I'm imaging an object or a scene at different rotations of that object, I can essentially just parameterize that as a function of azimuth angle for that object. For the solar, what I call the solar positioning system, same kind of thing. I can parameterize the lighting in different ways to where I can either just, you can think now I've got a hemisphere where I can place this light, so I can just parameterize as where I want to position the light as a function of azimuth and elevation angle, or I can parameterize it by date, time, and location. So I can just plug in a GPS location, date and time, and then I can say, well, actually, I want to calculate the position of the sun as a function, maybe in 10-degree steps, so I can look at for a certain location on Earth, date and time, like what the solar path would be and stuff like that. But there's lots of different things that we can do, and it gives me a nice summary of all the different positioning, all the different images it's going to take as a function of those geometries. Gives me a nice summary and approximately how long it should take to do the data collection. And then for each one, I can parameterize the lights, if I want to, so maybe during low solar elevation angles, you would expect near sunset, the light to disperse more and be more red, as opposed to if you're at solar noon, you would expect a much cooler color temperature. So it can do those types of things. Outside, a lot of times when we're doing experiments, it would be great if we could just kind of temporarily turn the sun off and only collect the downwelling light. Not easy to do outside, but we can do that type of stuff in the lab. So you can build as many lighting profiles as you want during the experimental collections and things like that. And then, we close the curtain and just tell it to go, and then the room will just spend however long it needs collecting your parameterized data set. And, I have a little webcam in there so we can kind of watch what's going on or monitor things remotely if we need to. On the data management side, I realized, we're going to be producing lots of data. So I decided to kind of build my own file format, for better or worse, that I call the ASL, the Applied Sensing Lab file format. And I kind of modeled it. I'm sure a lot of you are familiar with ENVI, to where, they kind of store the raw binary data in a raw binary file, and then they have a corresponding ASCII header. So it's a similar kind of flavor with ASL files. But I kind of build and maintain this all in C++, and then with any of our data sets, I provide MATLAB and Python readers. But basically, I just wanted something that I could streamline across our entire laboratory ecosystem. So our drone, like the flight computers I've built for our drones, export in this format just the same as our laboratory framework does. So here's just a couple of examples of very simple experiments. This is just showing a time lapse of, so I picked, I guess, the location of my lab in Google Earth and picked a date and time, and just picked from sunrise to sunset in 15-minute steps. And then we can just see on the right, here's what the corresponding polarimetric, in this case, polarimetric images look like. Here would be another experiment where it said, now I have a fixed sensor and a fixed solar geometry, but then I just want to rotate an object. So maybe for something like an object characterization type example. Here would be another one with just a little bit more complicated experiment where I'm just showing one where I'm essentially turning the collimated light on and off, because in this case, I wanted to be able to separate kind of the downwelling and specular components of the light. But this is also, there's a checkbox I can check to be able to couple the solar and scene geometries. That way you can see as the scene is turning, so as the sun is turning with it, so that it preserves the location of the shadows and things like that. So then we can do things like, if I extract the frames in the right way, we can simulate the camera movement, right? So maybe like a drone orbit or something along that line. But it is nice. Now, of course, we're all very close, so we don't really have much in way of atmospheric phenomenology, but I always figure we could simulate that if need be. But it does do nice things, like it gives us glints and other sort of realistic things. On the data truthing front, it would be great if I could automate some of this, but some of the data collections that we've done, we usually do a lot of this annotation using tools like RoboFlow and other sorts of things. There's some great online tools for doing this kind of stuff. So a lot of the data sets that we curate and are releasing, that we've taken in the lab, we've spent a lot of time doing these types of annotations. And I also have some other tools where I've built some kind of basic ray tracing tools. And the whole idea, most of these models, we use our light projection scanner to get a 3D model. And then these tools just allow me to load the 3D model in and kind of get them registered. The models get projected onto the image data, so that we can kind of get them aligned. And then once we have that, then we can generate depth maps and surface normal maps and other sorts of things that we particularly care about when it comes to polarization. Ideally, maybe before I retire, I would like to roll these tools in to where, with the precision of the lab, with all the different positioning devices, they are pretty accurate and repeatable. I would like to be able to do this to where you set this up and get your registration done kind of at the start of an experiment. And because we know how we're moving everything around in the room, as the data collection is happening, I would love to be able to export these types of additional products that are just generated from the 3D models and things, but it's, only so much time. So anyway, so we've started to build, or just as we're setting up and doing these experiments to support my students' research, and we go through all this trouble, the idea is that we can start to release some of these data sets. So these were, I think, back in, I don't know, at one of the SPIE conferences last year, I talked about, and we released a couple of these data sets that I called the ASL 2025. So these are all available for download today. But one I call the model desert terrain monochromatic DOT data set. The other one I call the model parking lot. So you've seen some examples of both of those. So I guess I'm kind of doing this in reverse order. But this, the parking lot model that you'll see here in a little bit was just kind of the first model that we worked to create, where we really, everything was accurately designed to like kind of civil engineering standards, and then 3D printed, and then I just basically painted, so it's just ABS plastic painted with acrylic paints or whatever. So I don't really expect pavement to look like that, right? It's not spectrally accurate, but it is spatially accurate, and it served the purposes of what we were doing with the data set. For this model, though, I tried to take it a step up to where it's just a simple kind of desert terrain. So you can see the 3D model here. There's some terrain roll to it, things like that. But then we tried to cover this model with more specular, my mouth is dry, I'm sorry, spectrally accurate materials. And so we tried to use real sand, or, our little plants, our actual dry vegetation. We just tried to use just natural materials to kind of create this. There are a few things like the little razor wire fence. I did 3D print the posts. Our model vehicles, we kind of painted ourselves with an airbrush, trying to use paints that may be more diffuse and as it would be expected on maybe an actual military vehicle. The tents, I won't tell you how long I spent making this crazy little tent, but I bought real panels of tent vinyl and put them together, things like that, just so that we're hopefully doing something that's a bit more realistic. And then same thing with I wanted to kind of simulate a typical target panel array that we would do in these types of collections. So some of them are 3D printed and shaped. Some of them are made of aluminum, and just used a different set of paint markers to coat them. And then the little reflectance panels are actual. I ripped these from the LabSphere guys at an SPIE conference, but they had little samples of just their permaflex panels. And I'm like, ooh, I could use those. So kind of useful. And then we have like a fairly large and growing model library. I mean, these are just simple, cheap die-cast vehicles. So again, from a spectrally accurate standpoint, they're not painted with automotive paints that have 7 layers of clear coat, things like that. But I think for many of the experiments that we're doing, they're good enough. So for this data set, and if I have time, I'll quickly talk through like why we collected this to begin with. But we just basically created eight different scenarios. So some that have just vehicles, some that have vehicles and some of these little flat panel targets, and then some that have no vehicles and just panel targets. And then it's just showing the lab setup. For this particular one, we chose to collect with a broadband monochromatic polarimeter. I have this is a spectral polarimeter that can actually collect at different spectral bands, but we just wanted to collect visible monochromatic polarization data. And with this sensor, it allows us to get full resolution polarimetric data, essentially. But as far as the experiment itself, we chose 8 different scene geometries, or 8 different azimuthal rotations of the scene. We picked 7 different azimuth and 5 different elevations for our collimated light source. So that gives us 35 different illuminations. And then we did this at 2 different sensor geometries, as you can see here. We also added a 36th illumination where we turned the collimated source off and just collected a diffuse light. So for this data set, you can see that's 8 scenarios, 2 views per scenarios gives us 16 views of the scene at 36 different illumination geometries. So overall, for each scenario, that gives us 560 full linear Stokes images, polarimetric images of the scene. overall for 128 unique views. And this is just some parameters for the sensor, which I'll skip over. But this is just showing, for this example, scenario one at the, first sensor elevation, this is showing a combination of direct plus diffuse illumination. So there's 280 frames in this sequence, and this is just showing the S0, which is effectively the unpolarized image. And then DOLP and AOP, you can just think of that as polarization, magnitude, and phase, essentially. But we obviously have a very highly parameterized data set, and we have this all annotated in what we released. So instead of looking at it as a video, here's just an example showing essentially some of the same data for one of those looks. So here's S0, S1, and S2. That's the polarimetric Stokes vector. Think of that as like rectangular coordinates. And then this is just showing here's, for this particular scene, we're looking at the polarization signature across all 36 different, or all 35 different solar illumination geometries. So we can see how the polarization signature changes as a function of illumination, for example, in this case. So again, we've gone through and done all the annotations. So for this data set, I think we ended up with about 70 target labels. So even though we were collecting with monochromatic sensors, we still annotated the targets according to their color and shape and other sorts of things, and of course, based upon their vehicle IDs and stuff like that. So, and with the data set, we provide a lot of other metadata where we've done some further annotating, and we took a lot of ground truth images of the scene because in some cases, right, where the targets are hidden inside the tent or under tables or vehicles, things like that. So that's the first data set that we had released last year. The second one, I think not as much care was taken. It was kind of our first one, but we were doing some vehicle telemetry estimation, like AI-based polarimetric vehicle telemetry estimation type data. So that's part of why we built this model parking lot as our first model, thinking that, eventually when I get my sensors airborne, which is happening now, it would be pretty easy to basically set up some vehicles in a parking lot and fly a drone orbit around them or something like that. So we built this model. Again, this one was not really meant to be as spectrally accurate. We were just trying to get something that was more, spatially accurate. But for this data collection, we did 28 different scenarios where we had some configurations of our vehicles that were dense, some that were moderately dense, and some that were sparse. So we just had 28 different scenarios. And here's again showing the scene. For this one, we used a division of focal plane RGB polarimeter. So this one essentially gives us color and polarization for this data collection. And similar to before, the way we parameterized the experiments, we collected on 36 different scene geometries. We only did 7 different like direct solar geometry. I'm sorry, 3 times 4 is 12. 12 different solar illuminations, and that at 2 different sensor geometries. But we also did 2 different diffuse illuminations, one with the collimated source off, but just showing, basically with kind of higher SNR conditions to show, like kind of mimicking like if it was a bright cloudy day, as opposed to a second one where the light is much lower with a much warmer color temperature, kind of mimicking like maybe dusk or civil twilight type conditions. But this is just showing, again, some of the data. This is showing one of the diffuse lighting examples. And in this case, we did our annotation just by vehicle class, not by individual labels. I wish my students would have done that. I didn't realize until it was too late. And this is just showing the second diffuse illumination. So compared to the first, we can see, this is the higher SNR case versus the lower SNR. We see much noisier conditions inside of, say, our angle of polarization images. And then this is just showing the different, with the direct illumination on. So I think I skipped over it, but overall, I think that data set has about 14,000 images, something along that line. So they're pretty substantial data sets. So to switch gears a little bit, so that's kind of the ARSSS lab and what we're doing in there and the types of data collections that we're aiming to collect there. And then of course a lot of that is to help with augment what we're actually going to do in the field. So this is the shuttle bus I had mentioned that I procured. So after a couple of years of hacking on it, I um, now it looks a lot nicer since I've got it wrapped and things like that. But I've added a lot of things. Like one of the first things I did was put 2,400 watts of solar panels on the roof. It's got cellular connectivity. I kept the lifts so we can lift our stuff into it. I've cut a lot of holes so we have external power and Ethernet and all that kind of stuff. We've got weather station. But inside, the idea was, we want this to be our field support vehicle to support any kind of data collection, but particularly to support our airborne, our drone flights and things like that. It's got a separate kind of HVAC system in it that runs off the power system, server cabinets, workbench, and just specialized storage, like particularly for getting our calibration panels like to and from places safely. It's got a kind of this large battery lithium ion system that the solar is charging, but we can plug a generator in, we can plug shore power in, all that sort of stuff. And then there's the ground control station that allows us we have a couple PCs in there for field processing and things like that, but then also some monitors so we can mirror our pilot cameras and payload cameras and all that good stuff. So this is our Alta-X drone that I've started building, several different payloads for that I'll talk a little bit more about. But I've also added some other things to the shuttle to where, I can take our gimbal and I can pop it on the shuttle and we can drive around and do sort of terrestrial or moving vehicle type collections. I won't spend too much time on it, but I've spent a lot of time, kind of building up some custom control solutions so we can send signals up to the payload while it's in the air. And, the software that I wrote, the flight computer software gets kind of transmitted down so we can see live feeds from the cameras and things like that. So I'll talk a little bit about it, but when the ROCX data collection that was hosted at RIT back in September, this was the payload that I brought and flew. So you can see it's a 3-camera polarization payload. So it has a visible shortwave infrared and longwave infrared polarization camera that all collect simultaneously. We also have a payload for our SWIR hyperspectral camera as well. But this is just showing the flight computer that I kind of built from the ground up, just showing that, to the person who's operating the gimbal and then looking at the live feeds, you can, with the custom controller I built, you can kind of flip through the different cameras, or look at them all simultaneously. It'll give you a lot of information. I guess I didn't have the storage device plugged in, but it'll tell you like when you're recording, and then if so, how many frames it's recorded, all that kind of stuff. Gives us live telemetry from our GPS IMU, and then it also gives you an indicator that shows, not only where we're pointing, but also where the sun is, just which is particularly useful for polarimetric data collections and things like that. So, but this is just showing for, come on now. I swear this played like right before I started. Kind of crazy. So, but this is just showing, from each one this is the raw data from each one of our of those cameras. I really can't believe this isn't playing. Well, this doesn't make any sense. So, well, anyway, this should be playing in it.
Right, slide.
I mean, I have the videos externally. I just don't understand why they're not showing. Yeah, I think I realize that folks online can't see, but I'll try to change that. It's really strange. But yeah, I have it's nice.
Just tap the share your desktop.
Yeah, let me go back to. Well, this might be somewhere in the registration process, but it's just showing. This is after I've done some cropping of the field of views. But this is essentially just showing the raw data from the visible shortwave infrared and long wave infrared sensors. But initially, they're just running on separate threads on the flight computer, so it's just time stamping the frames. So they need, if you just play them through, the frame rates were slightly different, and the field of views on the lenses were slightly different. So I've been working through getting both temporal and spatial registration of these different frames, and that's what I will kind of show here. So this is after going through that effort, and this is just basically taking the the average visible, because we actually had an RGB polarization camera that we flew, but it's just taking the average visible SWIR and long wave data and getting it all sort of co-registered temporally and spatially, and just we were pretty excited to this is the first time we flew this trio of sensors to see like actual co-registered polarimetric data. And this is actually just showing the S0, the unpolarized data. We're still working through getting the polarimetric data process. So we think this are going to result in some pretty interesting data by the end that we're excited to distribute as part of the ROCX data collection. And I told John, who's giving a talk in 2 weeks, just because I just assumed everybody at RIT knows everything about ROCX, and I guess that's not true. So John's talk in 2 weeks is really going to cover that. So I'm kind of preemptively giving a little bit of um, a taste of what we did there. I'm going to try this one more time. I was just watching these work right before my talk, so I really don't understand. But we flew this sensor through a number of the different experiments. So I think we ended up with some pretty interesting data sets. Like actually that's the wrong one. So this was actually Emmett's experiment was the UXO, so this is flying over the minefield. So I think there's going to be a lot of really, fun and interesting data to look at. There's also the something that wasn't planned that we ended up looking at kind of at the last second was we lifted up our drone to watch some other drones. So I think we've got some really great air-to-air kind of drone-based data. So there's a lot of neat data sets that I think that are going to come out of this. So anyway. So, but for me, like since I think I got my Part 107 pilot license back in the summer, right? So this was like one of the first exciting times that we actually drove the shuttle somewhere and flew the drone to do something fun and exciting. So, well, I realized I should probably, I knew I had more stuff than I really needed. So I'll just try to kind of slow down here, or just conclude quickly. But a lot of these different data sets, because I work a lot in polarization, some of the work that we've been doing is just coming up with looking at novel ways to do polarimetric fusion. Polarization data is even those of us who've been in the community for a long time, I think it's still kind of difficult, non-intuitive data to look at, and even people who've done this their whole careers, like I think a lot of times are surprised with what they see, and it's a really hard sell outside the community to like we see really great things with polarization, but sometimes it's hard to kind of like show the value of it sometimes. So I think through coming up with novel display strategies and stuff is something that we're looking on as far as instead of looking at raw polarimetric data. We want to look at how do we take S0 and find better ways to fuse in polarimetric information that still maintains that the natural look and feel of, say, a visible image, or things like that. So we've been working a lot in this area. Some of these strategies, it's a really common thing with polarization to use color to represent polarization, but if you do that, then you're not using color to represent spectral information. So by looking at some of these strategies, we can preserve color for true spectral color while rolling in the polarimetric information and more interesting things. So part of why we did the desert model collection was to support some of this fusion type these fusion development of these types of polarization fusion strategies. So we've looked at it's kind of novel ways to maximally extract polarimetric information and present it in kind of new ways that are more conducive for fusion type work. And so I'll kind of skip through most of that. And then the other thing the other example is, we've also looked at kind of doing more empirical ways of doing polarimetric BRDF type measurements. So this was showing some work we did a few years back on, using polarimetric imaging cameras with sort of 3D topology type objects, so we can simultaneously measure different facets under different geometries, right? So this was a really simple manual rig that we came up with, and then we imaged these objects as a function of location. But now that I have the ARSSS lab, we can turn the downwelling lights off and just look at the direct solar component of the light. And of course, we can control where the sun is and do these same types of measurements. So we did that. We did some outdoor collections and then repeated them inside the ARSSS lab, and was just trying to show that we can essentially recreate similar conditions in the lab as we got outside to be able to do these BRDF type extractions. And we were just able to show for at least 6 different paints that we can do pretty equivalent measurements indoors and outdoors for these types of things. But that's a talk in and of itself. And just overall, just trying to show, we do all kinds of fun stuff, and it's been really exciting for me. I've spent so much time building all this. I've just been building, and to finally get our field capabilities online and to finally have our laboratory capabilities going, I think we're starting to do some really fun research. So just in conclusion, hopefully that gives you a feel for, the difference of Dayton. You're surrounded by all these amazing researchers here. Like, I'm kind of a one-man remote sensing shop at Dayton, trying to do, a little bit in all these different areas that everybody's working on here. But it's all been kind of fun, exciting stuff. But overall, our laboratory capability, I think, is kind of giving us something new and different in ways that we can kind of contribute to the remote sensing world, and the types of data products that we can, collect, right, with what I call these scene-generated products. And of course, our mobile lab and our field capabilities are really, a pretty recent thing, but we're finally starting to get out to do a lot of things. So I think some of the big questions, right? I build all these fancy models and I take all this data. I mean, it would be really great if what we're doing in the lab matches what we're doing outside, but we really haven't quantified that. So I think that would be kind of exciting to be able to go out in the real world, in the real application space, and take data and then see how much our laboratory products fall flat, like how, or how useful are they? It looks really fancy and cool, but maybe, those are questions that we're still working to kind of answer. I've got no end, if you've got money for me, I've got no end of how to spend it, upgrading different things in my lab, all that kind of stuff. But we're still working on all kinds of things, still characterizing things, still doing all that kind of fun stuff. But I really am excited to be here. I think there's a lot of great ways that we can, to find ways to collaborate and do all kinds of fun stuff. So I really appreciate you guys bringing me up. And with that, I will say thank you and leave some time for questions. But I do appreciate being here. So thank you.
Yeah, question. Dave, are you going to build a mini system?
Well, yeah, when we brought our LiDAR sensor there, so we actually do have a pretty high fidelity model. And I think that would be a great idea. Like I've got all these 3D printers, why not? You know? Yeah, I think that would be really cool. I was just excited, like, and that was one of these experiments that kind of, it's like, wow, the Tate looks so polarized, and we didn't expect that. And I'm like, let's just do an orbit around it. And you know, RIT had already asked us to kind of do a LiDAR scan. So I'm like, that could be a really cool structure from polarization sort of data set, you know, like that isn't constructed in the lab, but is actually done in the field. So, but I think that would be yet another cool way to do it. It does, and even the side would, you know, I don't know why, but it, you know, I don't know that I have a good answer, but it's just like, ooh, that looks really cool. Let's fly around it. You know?
I could imagine just running a ray across the ceiling and test what it could be. Like a plane. If we thought about taking it from the it could actually have simulate a flight of an airplane pistol test.
I think that would be a great idea. Like, I don't think we've specifically talked about doing it on a rail system. We've talked about doing it other ways, but I think that would be certainly something that would be worth considering. It is. Yeah. Yeah, I think, you know, because what I've been looking at, at first I was like, oh, it's kind of hard to put that on the robotic arm and have it do the scans or whatever. Apparently that's really hard to make a robotic arm do that anyway. So I've been looking at some of these, is it Himalaya? Some of these that use like the Fabry Perot to where we don't necessarily like, is that actually a good use of one of those within the lab? So we don't have to necessarily scan, but I think, yeah, I think that's better because I don't think it's as effective to do it on the robotic arm, but sure.
Kind of like going back to the late '80s for these people models. That's their one.
Sure.
That's their one counts.
Yeah. No.
Oh,
Well, thank you. It's fun. It's I don't know why I like building these little models. It's satisfying my like, I don't know, inner child or something. Yeah.
Yeah, very impressive work, really cool and great. It's great to see all this activity. You touched on this toward the end, and I know there's a lot more that's going to do, but I was thinking more about the verification and comparing the lab data to the real data. And you showed some pretty good comparisons on those spheres.
The BRDF targets, yeah.
BRDF targets, so on. One aspect of that I'm curious about is the absolute radiometry and the signal to noise ratio. I wonder if you've looked at, is the noise comparable to what we see in real data, or is the radiometry comparable to real data? Well, I know the curves are not the same as the sun, but are you getting intensities comparable?
Yeah, and I don't know if that is something we should look at like in a very quantifiable way. But I mean, but obviously there's less light than we would expect outside. So usually we're just accounting for that with longer integration times or those types of things. But that fundamentally is different, you know, from doing it outdoors. And I agree, that's a great question to ask. I think, yeah, I don't know that we have the answer on the radiometry side either. But I think those are all things that we're interested in sort of looking at and doing, right? Because
probably at least compared to the SMR.
yeah. And that's probably true. I mean, because I think you could say like if this really worked, right? Because I don't have that answer yet to say, but it's pretty cheap to build a model, and then now we can parameterize it. You know, if you're trying to train an AI model to be robust to the typical variance that we expect to see in real collections, like can we capture that? You know, but if you could do that and train models, and then it actually works on the real application, that's a hugely useful result. And I think we're just really getting all this stuff online to where we actually can start probing those, you know, problems and trying to answer those questions. So yeah.
It sounds like you're creating data sets that allow you to like prototype or even augment other real world data sets. You can use machine learning algorithms to solve problems like those spatial reconstruction.
Yeah.
So I guess, and you've already told us about some like the short-term problems we're going to solve. But, you're still. I also have to say, awesome. It's really cool stuff. Very cool system. Huge amount of effort. So I'm curious, what do you think like the long-term problems are? Once you solve all the problems, you've got the money, you've got the right paints, you've done some validation, and you've got your data sets. What do you think the long-term problems are for developing models using your artificial data sets that will work in the real world?
I think that's a good question. I think because that is one use case that I've thought, and I know that's a big, because AI is essentially run out of data, right? Like they're out of data. So, I've gone to a lot of these talks where they really are focused on how do we use, augment with synthetic data. And like time and time again, you see that it's just not really working or it's not good enough. It kind of works sometimes, so that's where I'm hoping, is what I'm doing, since it's sort of this middle ground, is that a way we could really contribute? So that I think about that sort of a lot, but I think we just still need to get to the point to show that, hey, this is actually useful. But then as far as, like I said, I presented them backwards, but, at first it was like, let's just build a simple model that looks like what we want it to look like, knowing it's probably polarimetrically and spectrally not that great, right? That's where I would think with the model building side, like what can we do? Because ultimately, like the GSDs are way different than what we would expect outside. And yeah, we can change the lenses and do other things, but there's still, things that we can't capture in the lab, like certainly not atmospheric effects, right? If we were imaging from, 10,000 feet, like we would have to actually simulate all of that stuff on our data, which in some ways it's kind of nice to have the backward problem of like, well, we've got the high fidelity full resolution before the atmosphere has kind of messed us up. Like at least we know we've got the really high fidelity data that we know what we want to get to. And if we muck it up, then that's what we're, hoping to recover from the data. But yeah, I don't know. But I think that's really a big part of it, is like you want to get to high fidelity. If we were going to do this model based, like what can we do to make them as realistic as we would expect, or how real do they need to be in order to be useful? It's maybe a better question of the way I think about it, right? Because as we always know, like simulations are always like, there's things that my lab's never going to be able to do. There's things that DeerSig's not going to be able to do, or the problems with real data, right? So it's like always trying to figure out what is good enough to solve the problems that we actually care about. And I don't know that I know that yet. But hopefully what we're doing is useful in some way to someone.
I'm sure even if it doesn't work in the real world, more prototype that then you might be able to train on real data.
It's certainly interesting from like a phenomenology perspective. Like even if we're like, you just want to see, even if this isn't the ultimate, it's not a real car, but I want to understand, but it's pretty close, right? It's specular paint. It's, it looks like polarimetrically, it looks pretty believable. And it's doing the same thing that maybe this, what a real car would do. But it's not exactly what a real car would do because it's just different. But the idea is like, but it's still, from a phenomenology standpoint, it's still acting pretty reasonable. And this is data that I really couldn't easily collect outside, so at least from that perspective, it's giving us something different and new. Because I think a lot of times, like, could what I'm doing be a useful way to help DeerSig validate stuff, and then vice versa? Because that's where I'm like, I really need to go get DeerSig so I can have that as a tool. I feel like that's a tool I'm missing that I should be incorporating into what I'm doing in the lab, just as a first principles sort of prediction of, what we're doing. So, thank you. Yeah, thanks.
Any last questions? Sure.
I'm curious if you entertain the idea of adding a bias on this, like maybe a small part.
I think I have thought about that. And I think that would be, really cool. And it would be nice to be able to have like a model that can change itself, because I even think like if I ever wanted to look at doing this, thermally or things like that, if you have little objects that could heat up and cool down and do things like that. But I haven't probably thought more about it than other than wouldn't that be nice to be able to incorporate that type of stuff? so I would be very interested in all those things, and that's a cool idea. So
Getting the local model railroad talking about, or people getting kicked off campuses, FBI.
well, it's funny is like when I was um when my oldest is now 15, when he was 2, I think as a kid I always wanted to like build an HO model railroad, never did. So I started like I actually have this table in my basement that I started, and I spent way too much money on modeling materials, and then I just got too busy and never finished it. So most of the stuff you're seeing on these models, I'm like, I can finally use the thousands of dollars of modeling crap that I bought to do all this stuff. So it really is like satisfying to me. Um, I'm sorry.
There's a question online.
Okay,
You want to just read that?
sure.
And then was there one more? Well, I thought, and then we'll call.
Okay. So question online from Faye Zhang, like 2 questions. How you see your lab generated data sets positioned relative to fully synthetic simulations from game engines or rendering platforms like Blender? Do they tend to serve different purposes? And for the researchers who use your data, what properties of the data set seem to matter most in practice? For example, radiometric accuracy or scene diversity. So I think for the first one, or I guess they're both kind of related in the sense that I guess the way I look at doing things, I mean, obviously we're looking at, the physical world with real objects, and we're using real photons and real sensors and all that sort of things. So I would like to think that what we're doing at least is representative of reality. So how does that compare to game rendering engines? I don't know. I think when it comes to doing a lot of those renderings and stuff, they cut a lot of corners for all they really care about is that it's visually pleasing and not necessarily like what DeerSig would give us, right? In the sense that you actually care about radiometry or that things are accurate or incorrect. So I don't know. I guess I haven't thought about, but I guess I've thought about that from the perspective of, could what we're doing, especially since a lot of rendering engines kind of ignore polarization, but for a lot of materials, folks are starting to realize maybe we actually need to be thinking about polarization in order to make our rendering a little bit better. So I've thought about it from that perspective of, could what we're doing, from an empirical perspective, help inform some of the, making some of these rendering engines better, but I don't know. And then I think what properties of the data set, I think that for question 2, I think that just depends on what you're doing, right? So I think if all you're really looking to do is maybe train an AI system to detect cars or something like that, then maybe not having a spectrally realistic or a polarimetrically realistic model, it doesn't really matter. Like I think if spatially you train on a bunch of these cars, because I know some of the folks that I've been working with, in some of these data sets, we're always looking at them and they're like, wait a minute, I can't tell, is this a real car or is this from your lab? So it's like, it's kind of a good sign that, what we're doing looks pretty believable. And I would think, well, if your goal is to train an AI algorithm to detect cars, it probably would transfer pretty well to real data at some level. But now if you change the problem to something that actually where radiometry matters or where, just it's kind of like the problem with spectral, right? It's like, well, to do detections, it's not as difficult as if you're trying to do ID, right? Because now the spectrum matters. Like you need to be in reflectance, you need to be in all these things, but sometimes, so I guess what I'm saying is it's just going to depend, on. I have a feeling like there's going to be some applications that if your phenomenology is way off, like it's probably not going to work very well, and you'd have to work harder to make your model more accurate for those cases. So, sorry, it's a long answer.
Very much. Question, Will.
Yeah.
So, DeerSig's ability to do polarization is very heavily tied to, maybe, what I remember in the Modtran 4P, sort of a spectral
Yeah.
version of Modtran. Do you have any insights on what has happened in terms of polarization modeling beyond Modtran 4P?
I know
What has SFI done? Have they done anything with that?
from everything that I've heard, you know, the next version of Modtran, which is what, the 6? It's supposed to have full polarization. But I know it seems like it's, you know, it's coming, but then it keeps getting pushed. But you're right, because I know when we first, the BRDF work was actually an Army project. It was like during maybe 2020 or 2021. And the company I partnered with, the guy had, you know, he had DeerSig. So we tried to do some initial testing, and we went through this process that took longer than the entire grant to be able to get Modtran 4P. So it was really painful, and something that, yeah. So you're right. Like, I really hope that, because we haven't paid for Modtran yet, but I think that's something I also need to get going and pay for in my life. I know enough people usually that can run Modtran to get a SPY, but I think I keep waiting until it comes out so that I'm like, oh, well, when they actually have the polarized version of it, but maybe we'll be continuing to wait a long time. So yeah. Yeah, that's right. Yeah. And Modtran 6 with polarization. Yes.